All right, I'm going to show you how to add vectors graphically. So this would be using graph paper. So we want to do 3u minus 2v plus 5w. And let's go u, v, and w. So you almost need the graph paper or a grid to keep track of the length here. So my vectors have magnitude. Each square is 1 unit, and it also has a direction. And we're using the grid to give us the direction. So determine the resultant. So that means we're going to add them together. So I'm looking at this, and this is where I have the luxury of the smartboard, so it'll make it a little bit simpler for me. So here is 1u, and I'm adding 3 of them. So there's 2, there's 3. So there is 3u. Now I need negative 2v. I'm going to subtract 2v. If you're subtracting a vector, so I'm going to take my v vector, clone it. My v vector is not going to go in that direction. It's actually going to go in the opposite direction. So instead of going over 2, down 2, it's going to swing around and go up 2 to the left 2. So there is a negative v, and I go up 1 more pair to get my negative 2v. So the negative changes our direction, changes the direction. Alright, so just keep that in mind when you have a negative. When we do algebraic method coming up, you'll find that it all falls out for us, so you don't have to worry about it. And finally, I need plus 5w. So here's my w vector. So there's 1, 2, 3, 4, 5. So there is my, there is my 5w. Definition of a resultant, my vector that goes from starting point to end point. So there is my resultant vector. So I want to determine the resultant. There it is. Now it's just some quick math here. So first thing, you always, if it says, and here's the key here, determine the resultant, it means that I need a magnitude and a direction. So I have to find the magnitude of r. So the magnitude of a vector is the square root of its x component squared and its y component squared. So in this case, from my starting point to my end point here, my x component is 2. So I'm just counting squares. My y value, I'm going down, so it'd be negative 1 squared, which gives me the square root of 5 units. So magnitude of r is root 5 units. Direction. And here's something that I do like about the geometric. I want to find this theta. When you do it geometrically, or you do it with a picture, you're always going to have the x and y component. So that means you have opposite and adjacent, which is your y value and your x value. So it's always going to be, for direction, tan equals tan theta inverse of opposite over adjacent, or always your y component over your x component. Okay, and that's a formula that we're going to use over and over and over. So I'll just highlight these two formulas because this one as well we're going to be using quite a bit, especially when we get in the algebra, and you'll see why. So that means that we would have tan inverse of the y component, which was negative 1, and your x component was 2. And there you go. You're done. Don't have a calculator, so therefore r is root 5 units. And for a direction, if we're going to use the northeast, southwest, you would say from your starting point or your pivot point, you're going to face east. So east, you're going to turn whatever theta is toward the south. Okay, so you head east and you twist or pivot your way south theta, and theta is defined up above. So there you go. There's a geometric answer. Okay, drawbacks here. You always need graph paper. You always have to sketch it out at the right length or accurate lengths to do it. But it does lead us into algebraic form. So, algebraic vectors. To use algebraic vectors, we need to review the right angle triangle and discuss what's called components. So, if I come up with a vector on my very accurate xy axis, what we find, and I've been referring to it already, is that the length, when you create a right angle triangle, the length on the x-axis is what I call the x component, and I'm just going to refer to it as x. The length, or the altitude or height of the right angle triangle, this is what we refer to as the y component, or your y value, and that occurs for some angle theta. So if I use my primary trig ratios, talk about the x component for a second, in order to relate it back to what we're working on, and that is when we're dealing with the magnitude of a resultant, if we use our primary trig ratios, we find that the x component is our adjacent side, y component is the opposite, and the resultant is our hypotenuse. So the x component and the resultant, if we mix them together, we find that it is cos theta equals a over h, or cos theta equals, the adjacent side is just our x value or x component, and the hypotenuse is the magnitude, and I shouldn't really use r, let's just use vector u. It's going to be resultant sometimes, but it may also be just a vector in general. Okay, rearranging it, our x component is equal to the magnitude of u cos theta. So very, very important. If I look at the y component, now we're using opposite, so sine theta equals O over h, and sine theta would equal the y component over the magnitude of u. Got a little bit more room here. So that would mean that y equals magnitude of u sine theta. So there are our components. So what does that mean? It means that for a vector in algebraic form, or a vector in algebraic form, you can write it two ways. So the u vector could be written as magnitude of u cos theta I, so this is unit vector form, plus magnitude of u sine theta j. Okay? Or if you are going to work in coordinate form, magnitude of u cos theta with a comma, magnitude of u sine theta bracket. Okay? You can break any vector down. So this definitely, absolute, must get on your cheat sheet, because when you're using algebraic form, you're going to be using one or the other. All right? And I have a series of examples coming up where we'll talk about this.